respect to the non-interacting band insulator. It doesn't have P, but should have 1 plus P. So you would then say in this momentum space picture, as the holes move around, in fact, there would now also be double occupancy. This will be allowed in the picture in momentum space. You would say the Hall effect should correspond to density 1 plus P. So there's two very, very different views. But at very low doping, you expect density P, and high density, you expect density 1 plus P. And in fact, if you do photo emission, this is, you send in light and you look at the electrons coming out, you can map out the Fermi surface. So this is the boundary between the occupied and unoccupied states. These are all the occupied states. And if you look at the density of occupied states, it turns out to be exactly 1 minus P. And therefore, the density of holes, as seen in this experiment at high doping, is indeed 1 plus P. So that's the basic theme of the whole talk. How do you go from P to 1 plus P? What kind of quantum phase transition is it? And why is it so crucial for the properties of the cuprate superconductors? So here's some other data, more recent work showing you that there is indeed a sharp phase transition. Here's the specific heat measured in the normal state, and there seems to be a sharp peak at some critical doping. Here's the Hall number, which is supposed to be proportional, which is positive, proportional to the carrier density, and you see that at low doping it's P, and at high doping it's 1 plus P. So there's some kind of quite sharp crossover. And finally, I want to mention this not yet published work, which is really in some ways the most remarkable. So what they measure here is something called angle-dependent magnetoresistance. So here's the momentum space Fermi surface of the material. You apply a field at some strange angle, theta, and then you measure how the resistance varies as a function of angle. So from this variation as a function of angle, you can read off something about what the Fermi surface looked like. So if you do this at high doping, you find that this particular Fermi surface here does an excellent job of fitting the data. So this Fermi surface here that I'm showing you is basically the same as this one here at somewhat different values of P. So this is the high doping picture where the free electron model works, and you get exactly what you expect by just ignoring. So density functional theory would just completely give you the right answer immediately. However, if you look at low doping, then you find these full lines here, I believe, are the theoretical fits. The dashed line is the data. So if you take at that density the corresponding shape of the Fermi surface with density 1 plus P, it simply doesn't work at all. This is some other model corresponding to small hole pockets that doesn't work very well either. What does work is this one. This is now the Fermi surfaces are small, so I'll refer to this as a small Fermi surface, and that fits the data beautifully. The only catch in the picture is that to get this Fermi surface, at least naively in the 1 electron picture, this is the Fermi surface you would expect if there was long-range antiferromagnetic order. So I mentioned this antiferromagnetic phase way back here. So I said there was an antiferromagnetic phase here. If that order was present all the way up to here, and there'd be no problem, you'd understand the data. But it's not. There's something very bizarre going on in this region. It looks as if, as far as the hole density is concerned, that it's holes in an antiferromagnet, but there is no antiferromagnetism. The spins are quantum fluctuating, but nevertheless, there seem to be two different metals between which there's a phase transition between, say, here and here, and also in this ADMR data. Okay, I don't know what the value of PC they found was, but it's around the same value. It depends a little bit on which compound you're looking at. All right, so that's the introduction of my talk, where I just highlighted some key pieces of data, according to me. I'll pause quickly for any questions on the base, what is the basic issue that we're addressing. So any questions? Okay, all right, great. So then I'll proceed. Oh, sorry. I forgot to mention one more piece of data. This is again very recent work, just about to come out in Nature Physics. This is a measurement of a nuclear magnetic resonance. And they have some ideas on what this hidden magnetism is. And they claim it's some kind of spin glassy order, but very weak, which is present in high fields. By itself is not sufficient to explain the ADMR data. But okay, it's a hint as to what you should be thinking about. All right, so now I'll start the main part of my talk. So I'll begin by talking about a non-random model, just give you some basic ideas. I won't go into any detail. And then I'll talk about some highly simplified models with lots of randomness. And this is amazingly one of those situations that making things random actually simplifies the situation, and you can make quite substantial progress in the random models. So I'll come to that next. So let me just at least introduce the idea of metal-to-metal transitions in non-random models. Okay, what did I do here? Okay, yeah. So there is actually quite a well-studied example of a metal-to-metal transition, but that happens in so-called Condo lattice models. So in the Condo lattice models, you have two types of electrons or two types of atoms on which the electrons are moving. This is a caricature of Condo lattice. So there are the F electrons that sit on these darker circles. And the property of the darker circles is that there's lots of Coulomb repulsion. And so there's always exactly one F electron per site. So it's really like an insulator, the F sites. But then there's the mobile electrons, which I call the C electrons of the conduction band. And let's say they have some density P. So not every site is occupied, they're just moving around merrily. Whereas here on the F sites, there's only fixed spins. Now the Condo effect, which is driven by this exchange coupling J Condo, tells you that when you have a spin coupled to mobile electrons, that spin gets screened and effectively becomes part of the continuum of excitations of the Fermi liquid that's surrounding it. And there's a simple extension of that theory to the Condo lattice, which really says that basically, even though these electrons are immobile, they get swallowed up by the Fermi sea, and you do get what's called a large Fermi surface. That is, this is the so-called heavy fermion state, in which it's as if all the electrons are mobile, but they're very heavy. Okay. Okay, so there's again a long theory of that I don't want to go into, but I can at least tell you what a variational wave function for that state would be. Picture?
Yes.
All right, so this is where I was talking about Condo lattices.
Yes.
Okay, all right. So, so in the Condo lattice, then there's the conduction electrons that have density P, and there's exactly one electron per site on the F sites. And then what I was asserting was that there's a heavy Fermi liquid state where basically you can understand that, but just initially just ignoring the fact that the interaction between the electrons. So just think of the F as also free electrons. So you get a two-band model of C and F, and you just form a free fermion state between them. And then you say, well, actually, I have to remember that only one electron can occupy these sites. So you say, well, okay, well, I can just get rid of that by just dropping those components of the wave function. So that's a projection onto one F per site. And the understanding is when you do that self-consistently, you get this heavy electron Fermi liquid. But the important point is you get a metallic state in which the density of carriers is 1 plus P. So the 1 comes from the F, and the C comes from the mobile electrons. The P comes from the mobile electrons. Okay, so that's what's called the heavy fermion state. However, there's another state that's possible, which would be what's sometimes called FL star. And in that state, what happens is you do something very different. You separate, you really think as if there are two types of electrons. There's the mobile electrons, and then there's the conduction and the localized electrons.
And what the localized electron do is form a spin liquid, that they form singlets with each other. And these singlets can resonate in some way. So there's some complicated resonance of the F electrons. There's always one F electron per site. So these are really truly insulating. They form a spin liquid. And the C electrons move around. And so now the actual wave function will be a product of two components. There's the spin liquid of the F, and there's the free electrons of the C. And now the density of the mobile electrons is P, not 1 plus P. So this state is something that violates a theorem. There's a theorem called the Ludinger theorem that says that anytime you have a metal, the area enclosed by the Fermi surface should count all the electrons, mod 2. And it clearly doesn't. And the reason it's able to get away with that is because of what's called topological order. These spin liquid state here of the Fs have a certain topological order, and that allows you to exploit a loophole in the Ludinger theorem. So the complete story then is that you have two phases of matter. One is the Fermi liquid with a large Fermi surface. The other is FL star with a small Fermi surface. And there's actually a phase transition between them. So this is a novel type of phase transition in which there's no broken symmetry or anything, but it's a phase transition in a gauge theory. That is what, if you do a more sophisticated theory of this, turns out to be U1 gauge theory, where effectively you go from a Higgs phase on this side to some kind of deconfined phase on the other side. And so I don't have time to go into the details of all of that, but this is now fairly well understood, the nature of this transition between a small Fermi surface and large Fermi surface described by a gauge theory. But what makes this work really is the fact that you already, to begin with, you have two types of electrons. So you're able to exploit what could also be called a selective mod transition. That is, you select one type of electrons and freeze them, and the others are free to move around. And so when you freeze one type, you get a small Fermi surface. When you allow both to move, you get the large Fermi surface. So that's kind of very, in the end, it's not that complicated once you've worked out the structure of the details of the phase transition. However, in the cuprates, I mean, this is the essence of the difficulty. We don't have two types of electrons. There's only one band. And so it's not at all clear why should some of the electrons localize and others keep moving to get a density P of carriers. So that's really the heart of the mystery. And what is the nature of that transition? So I'm going to give you two different ways of thinking about this transition in a one-band model. One is due to Yahui Zhang, who's a postdoc at Harvard, which plays a little trick. So here's, and gives you at least a theory for how such a transition can happen in a one-band model. Again, I won't go into any detail other than just sketching the outlines of the argument. So here, this is the square lattice up here, the one-band Hubbard or TJ model I showed you earlier of the physical electrons. And now what we want to do is find a state of this electrons moving on this lattice in which some are mobile effectively and some are moving. How can you do that? How do you choose between them in some systematic way? Well, the way to do this, it turns out, and this is really something I've been searching for many years, and this is by far the cleanest way I found, or Yahui found really, is you exploit what are called ancilla qubits. So, this is a kind of idea that's quite common in quantum information theory, where you just imagine you have some extra qubits in which you can use to generate entanglement in the physical qubits. So here's our physical state. We want to write down some complicated entangled wave function for the physical electrons. And we don't have too many tools on how to do that, how to write wave functions. We have the BCS wave function, we have the Fermi liquid Slater determinants, we have the Laughlin state, and that's about it. I mean, if you wanted to write down some complicated correlated wave function, we don't have too many tools in writing down nice wave functions. So we're going to use this trick from quantum information where we add a few extra qubits, and that will allow us to write down a wave function for the physical layer, a new type of wave function, which will have exactly the right type of properties. And so the trick is that you introduce two hidden layers of qubits. These are just like the f electrons. Rather than having one f electron per site, you have two f electrons on each site. And the reason you want to do this is, if you introduce one f electron, you're really changing the problem. Then you've got the spin excitations of that f electron, and that's a different problem if you had an actual f electron here. But if you introduce two, the two of them can form a singlet with each other, which is JPerp. So we're going to assume JPerp is some large number. And so they're just going to form a singlet. And once they're frozen into singlets, they're as if they're not there. So there are these two spins, S1 and S2, which like to form singlets with each other. And they're just going to be our tools for us to form the other types of metallic states. So in particular, the simplest state you might imagine when JD is very small, this coupling between the physical layer and the hidden layers, is that these spins just form their own singlets. So this is like we haven't done much at all. These two states have formed singlets. And then the physical layer is just free electrons. So then our wave function, which is shown down here, has rung singlets of psi tilde. These are the singlets I showed you over here. And then just an ordinary stated determinant of the mobile electrons. So this will have density 1 plus p, because the density of the mobile electrons is 1 plus p. Okay, so that's the Fermi liquid phase, no big deal. The question is, how do I get a small Fermi surface out of this? Well, the way you do this is you're on a very different trial wave function. So now this new wave function, what you do is you make a slated determinant of C and psi. So this is just like the Condo lattice I just showed you. You had the mobile electrons and you had the F electron. You take the two of them and have them form, hybridize with each other. So you form a slated determinant of them. And these guys sitting here, these electrons, then you also form a slated determinant of the psi tildes, which are the lower layer, the second layer of that's hidden. And then finally, but this is now a wave function. These two terms are wave function of some more complicated state that I'm not really interested in. What I want is a wave function of the physical layer. So what I do is I take this complicated wave function and I project out everything into singlets. So I just drop all the terms here, which the hidden layers don't form a singlet. And you can show that this kind of state now has exactly the type of, small Fermi surface that I wanted. And why is that? Well, if you now look at these two layers which form their own slated determinant, how many electrons do they have? Well, they have electrons 1 here and 1 plus p here, which is 2 plus p. So the 2 plus p mod 2 is p. So effectively, in the end, you only have p carrier density modulo filled bands. On the other hand, there's still 1 electron per site sitting here. What is that? Well, they'll form a spin liquid, and that spin liquid could have low energy excitations. But that's kind of required, because if I didn't have this spin liquid here, I'd run into trouble with the Ludinger theorem. I have to have some topological order to allow me to violate the Ludinger theorem for the physical electrons. All right. Okay, so that's the basic picture. There's two papers with complicated gauge theories of the phase transition. Curiously, one of them is SU2 cross U1, much like the theory of electromagnetism and weak interactions. But of course, there's a big difference here. You also have Fermi surfaces floating around. It's not relativistically invariant. But you can read more about that. I won't say any more about this. Okay, I'm going to pause there then for any questions on that part of my talk. How does this work? I can't see anybody. Any questions? And I hope
think
around.
Before you pause it, Aries had a question. Hi Subir, was superconductivity suppressed by a magnetic field in the Hall measurements you showed us? I think was in the beginning of your talk.
Yes, the answer is yes. So let's see, you're talking about the angle-dependent magnetoresistance, ADMR? Yeah, so this is a cuprate with a relatively low DC, the neodymium strontium copper oxide. And yes, so I forget how large these magnetic fields are, but they are above HC2 for this material.
Actually, I was wondering about the previous slide.
Sorry?
I was wondering about the previous slide, the Hall measurement.
The Hall measurement. Yes, that's also true there too.
Okay.
Though some of those Hall measurements are in YBCO at 50 Tesla or something like that.
Okay, got it. Thanks.
Any other questions? All right, so now let me go to the random problem. So, we've looked at a relatively realistic problem, and it leads to some rather complicated gauge theories that I've mentioned over here. But we'd like to make more progress, especially also this phase transition that's not so easy to address numerically. So we want to work in models that are a little more tractable, but then hopefully have the same physics. And it turns out that a lot can be learned, and much of the physics is captured by a very simple looking model. So this is the model that will be the subject of the remainder of my talk. So this is it's a JHubbard model. So you have some electrons on n sites with some hopping and some exchange J, and a local Hubbard repulsion U sub H. Okay. And the key thing about it is that these Tij, and Jij are random numbers. So this means that, so here's a picture of it. So there's some n sites. Some sites are empty. Some sites have 1 electron spin pointing in some direction. Some sites have 2 electrons. And now from the Tij, the electron can hop from any site to any other site. So every one of those is an allowed process. And each one of those happens with some different random number Tij. Similarly, there can be a J where a pair of sites can exchange with each other. And each one of these J's has a different magnitude and sign. Okay, so that's the model, but the U is the same on every site. And then you send the number of sites to infinity. Every site can hop to every other site with a Tij. Every site can exchange with any other site with Jij. So really, we have a well-posed problem now. As a function of this 1 over U, let's say T squared and J squared are sum of order 1. And then as a function of 1 over U, and the doping density P, what is the phase diagram? So we want to fill in this phase diagram, and we want to do theory and maybe some numerical work, and really at least agree on this model, what is the ground state of this particular model. So first thing first, so first let's stick to half filling, that is 0 doping. Now at half filling, if your U is very small, means you're up here, then you can pretty much ignore the repulsion between the electrons. And the electrons are moving on a lot, and it turns out the Jij doesn't do very much. So you basically get a Fermi liquid. So you can solve for this region here, and you just get a Fermi liquid with some semicircular density of states approximately. And another property of a Fermi liquid is that its local electron Green's function decays as 1 over tau. This is just a Fourier transform of a constant density of states at the Fermi level. And furthermore, the spin correlations are basically, just a bubble diagram. It's just, so this goes as 1 over tau. Oops, this is doing some funny things here. Maybe I should. Yeah. So this thing goes as 1 over tau. Oops. No. Okay. Well, forget that. Yeah. So this goes as 1 over tau. Yeah, I shouldn't put my fingers on the screen. And the spin correlation will be a bubble. So that will also go as 1 over tau, and the spin correlation therefore decay as 1 over tau squared. Okay. So now you increase the value of U. As you increase the value of U, what you expect is at some value of U, the system will become an insulator, because this is the Mott-Hubbard transition, and you open a gap to the charges will not be able to move around. So let's keep increasing it even further. And if you increase it even further, what happened there? Yeah. then you have exactly 1 electron per site. And in that case, the only part of the Hamiltonian that will be active, which will be the exchange interaction. And this thing, this is exactly like what's called the Sherrington-Kirkpatrick model for a spin glass, but now this is spin a half spins, not classical spins. Okay, now that particular model has been studied numerically by Arakia and Rosenberg. And what they found was that it is indeed a spin glass. So just like the classical model at 0 temperature forms a spin glass, the quantum model seems to do the same thing. And what that means is that on every site, if you look at the spin autocorrelator, it has memory, it has infinite memory for at long times, and it's just frozen in its some orientation. Okay, so now what I want to focus on is some very nice recent work on the nature of this transition. What's happening here? Well, so that's been studied in this work by Cha et al., Peter Cha and others at Cornell and Flatiron. And they found a remarkable continuous phase transition, which had what they called SYK criticality. Of course, I have no objection to that. And the reason they called it that is because there's a certain other model, which is basically sort of like a SUM large M generalization of this antiferromagnet, insulating antiferromagnet, in which the spin correlation decay is 1 over tau. And a big part of the remainder of my talk will be trying to explain to you where this 1 over tau comes from. But what they found kind of amazingly, that there's a continuous metal insulator transition, and there's some kind of critical behavior of spin correlations here, which matches those found in certain other insulating antiferromagnets. And what we've shown in this work is this behavior has quite a robust property of large class of critical phase. Okay. So here's some of their data. So this is some data in imaginary time of the spin correlation Q of tau. It all fits beautifully to 1 over tau. I won't go into the details. Also, very nicely, they see a linear and T resistivity. We have some ideas on what's that due to, but not a complete understanding. And this goes on to very low temperatures, so that's also something that's observed experimentally. This 1 over tau spin correlation is sometimes called the marginal spectrum. So and this is also sometimes, seen experimentally, at least to the extent that the electrons look like marginal Fermi liquids in some experiments. So there are a lot of very nice features at this critical point between the metal and the insulator. And another kind of remarkable feature is that, as you go from here to here, there's 2 things happening at this critical point. Here you have a metal where the spin correlations decay to 0, so it's not a spin glass. Here you have an insulator where the spin correlations go to a constant, so you have spin glass order. And in between, you have this novel critical point that's going to be the focus of my talk. But what you see then are the 2 things happening at this critical point. One is you have an opening of a charge gap, and the other is the onset of spin glass order. These need not have happened at the same point. You could have had a metallic spin glass. There's nothing wrong with having a metal, which is also a spin glass. In fact, very soon I'm going to talk about such a state. But that doesn't seem to appear. So that suggests that there's some, this is a non-Landau type phase transition or deconfined critical point. Okay. And we'll find more evidence for that as we go along. All right. So now, of course, that's at 0 doping. And now the rest, I really, problem I introduced at the beginning of my talk was what happens as a function of doping P. What happens as along this axis here. Okay. So first of all, let's go to very large P. Then again, you have so many holes that the electrons hardly feel each other. So you again expect the same Fermi liquid behavior at large doping, just like you see in experiments. So what about at smaller doping? Well, we can make the conjecture that the spin glass order, which is an insulator here, when you dope it, will eventually will also survive in the spin glass, and then there'll be some phase transition at which the spin glass order disappears. And really, the remainder of my talk is to tell you about the nature of this transition, at least our ideas of what could be happening here, which turns out to fit very neatly with what's observed in the cuprates. Okay, so what do I do here? With very large U, basically, there's no double occupancy. So I can basically send U f sub h to infinity and only have these two terms. And that's what's called the TJ model. So here's the TJ model. I've sent U sub h to infinity, but I have a constraint that the number of electrons on each side must be less than or equal to 1. So here's a pictorial representation. There's 3 possible states on each side, empty, up, or down. And that's what happens. And the spins can point in any direction, and these empty sites can move around. And we want to solve this in the limit of Tij, and Jij are random variables. And it turns out you can make quite an amount of progress in solving this problem and even get some exact results. Okay, but before we get there, I'm still showing you some numerical work by Henry Shackleton and Alex Witek, who looked at what happens to the local spin correlation function, or the local spin susceptibility, which is basically SI of 0, SI of t, Fourier transformed. And if this has a peak at very low frequencies, as you see here at 0 doping, that's the doping there. There's a peak at low frequencies, that indicates the presence of spin glass order. So this particular peak very much matches the work of Arakia and Rosenberg. And what Henry and Alex did was look at higher doping. This is 1/6 doping, 1/4 doping, 1/3 doping. What you see by around 1/3, this peak has disappeared. So there's this phase transition with the vanishing of spin glass order around p equals 1/3. Okay, so that's, then I put this p equals 1/3 over here at the bottom. And what we want to now, we now have some evidence that that's what's happening, and we want to now understand what happens across this line. All right, so that's the problem I'm going to try to describe in the remaining time. How much time do I have? 15 minutes or even less. Okay, any questions then? Let me pause there for questions.
There was a question by Ilya. Let me unmute her. But she asked, what is the resistivity in a 0-dimensional SYK model?
Oh, excellent question. Yes, I kind of, yeah. So what do you mean by resistivity? Right. So I should have explained that. So what they're really doing here is not really looking at the model I described. They're looking at a slightly different model, which has essentially the same properties, where you take a model with non-random hopping on an infinite dimensional lattice. You take the hypercubic lattice in d dimensions and d to infinity, and then you take random Jij between native tables. So that's the model that you can solve, and it leads to essentially the same mean field equation. And for that model, you can define the resistivity quite clearly. So that's really what's plotted here. It's the resistancy, not precisely of the SYK type model, but of the or the random Hubbard model I showed you, but high dimensional versions.
So they were doing DMFT on this or something?
This would be more accurately called extended DMFT because of the exchange interaction.
Right. Okay.
So this is a model for which a version of extended DMFT is exact. Yes.
Mm-hmm. Yes.
And in fact, that's the next step of what I was going to describe.
All right.
So we'll come to that. Yeah. Other questions? Actually, can you, Krista, can the audience see my face? Because I can't see anybody.
Yes, we
Okay,
cannot see you.
Can you see me now? Oh, now? Maybe my finger was on the wrong bit. You can't see me?
No.
Oh, okay. Let me see. 1 second. Oh, I stopped it.
Now I can, yes. Now I can.
Okay.
Yes.
All right, good. Yeah, all right. So before I get to the TJ model, let's go back to the J model only. So there's just random spins with JIJ all, sorry.
I'm sorry, Subir. There is a question by Vladimir. Let me unmute him and then
Sure.
he can do the question himself.
Yeah, well, so hi, Subir. I have this
Hi.
question. You mentioned in the first part of the talk that the possibility for this non-trivial transition is because of topological order that can happen for these singlets.
Yes.
But in these models, but this usually topological order is specific to specific dimensions, like 2 dimensions. On the other hand, these random class of models, they live in high dimensions. So how is it possible that the 2 classes of problems have similar physics?
Okay, so topological order, yeah, was a loose word, but really more precisely what you need are emergent gauge fields. You need some low energy gauge fields to violate the Ludinger theorem. And that can happen in any dimension. The other point would be that in the large dimension limit, first of all, it's random. There is no concept of a Fermi surface, but you can have some sense of low carrier density versus high carrier density. And the gauge fields, in fact, you do, in the large dimension limit, the gauge fields effect is suppressed. They don't appear as explicit excitation, which is why that's easier to solve. But they're very much there. There is a fractionalization that I'm going to argue for that is present. So it's really fractionalization, more precisely, that's required. And that makes sense in any dimension.
Okay, thanks.
Other questions? All right, great. So now let me go to the random J model and just review what would be, what I did with Jinwoo Ye in '93 for a model of this type. So what we want to do is, take some, write some path integral formulation of this random Jij, and you can do that either using what are called these parton variables, either fermionic partons or bosonic partons. The answer shouldn't depend on which choice you make. And in fact, the answer I'm going to present doesn't depend on that. But for now, let's just think of them as an abstract spin. So what you do is you can write down a path integral for all of these spins. And the path integral for a spin has this famous Berry phase term, which is each spin is mapping out a path on the surface of a sphere. And there's a phase factor that appears in the path integral, which is the area that the spin maps out. So that's this term over here. And that's crucial to the whole argument. And then you get all these interactions between the spins which are random. And now the magic of the infinite range model is that you can average over all the exchange Jij. And in the end, the problem with n spins becomes equivalent to the problem of one spin. And so that's the one spin I focus on. That's kind of, rigorous in the large n limit. You can show the problem reduces the problem of one spin. What's not so rigorous is I've ignored here the replica indices. But since I'm not going to talk about the spin glass phase, that's also okay. So you have the path integral of just a single spin, which has a self-interaction. It has a time-dependent, retarded interaction between spin at time tau, spin at time tau prime. So that one spin is moving around on the surface of a sphere, and it's interacting with each other between different points on this path. And that interaction is some function q. So what is this function q? And this is the nature of dynamic and mean field theory, which in this case is extremely simple. This function q is the following, is determined by the following recipe. You work out, you evaluate in this path integral for some q, you're given a q, you pick a q, you work out the spin-spin correlation function. That will be some q bar. So this is something, you could numerically do in principle or do it, if you're very clever, you can do the path integral, but you can't. This is too complicated a path integral. Or you can take some large m limit, which is what we originally did in '93. And then the final answer is you get a solution. To find the solution of the original problem, you solve this equation, q equals q bar. So this is the self-consistency condition, which is the key to the whole game. All right, so this problem, as I said, is extremely hard to solve. So we're going to try to solve a simpler cousin of it. And that will be sufficient for my purposes today. So we just assume that there's some solution where Q decays with some power law alpha. So so gamma and alpha are unknown things that we have to determine. But we just make this ansatz for Q with some exponent. And then if you go back and look at this problem, you have some power law interaction. You can think of that power law interaction as coming from some other degrees of freedom. You can kind of do a Hubbard-Stranovic decoupling of this term. And in fact, you can write it as what's sometimes called the Bose-Condo problem. You have a single spin, S, coupled to some Bose field. And that Bose field lives in D spatial dimensions, where the spin is at the origin. And there's some exchange coupling between the spin and the free Bose field in D dimensions. And then you can see that you reproduce the original problem with this exponent alpha, provided you choose alpha equals D minus 1. That's just follows from the nature of the correlation function of a free Bose field, free relativistic Bose field in D dimensions. Okay, so this is the Bose-Condo problem. It's sort of like the fermion-Condo problem, where you have a single spin interacting to free fermions. Here, a single spin interacting with gapless free bosons. Okay, so this problem you can, in some respects, solve exactly. So first of all, you do the kind of RG procedure that you know from the Condo problem, and you find this kind of RG equation, 2 order gamma cubed, and there are corrections at higher orders. So you might, where epsilon is 2 minus alpha, that's where the system is under control. And if you look at this equation, you find that it has a fixed point at some value of gamma equals gamma star, where of order square root of epsilon. So that's great. Now this kind of RG flow is not really analogous to the Condo problem, where the J or the gamma just flows to infinity. This is more analogous to the multi-channel Condo problem. And that's that's a generic property of these Bose problems. They actually look more like the multi-channel Condo problem. Okay, so you do the RG, and you can, at this point, now figure out what is Q bar. Okay, here comes the magic, which I won't explain in any more detail. You can actually prove that Q bar to all, or even though you don't know the exact fixed point, you can prove to all orders in epsilon. It's 1 over T to the 2 minus alpha. And this comes from the fact that you have this Berry phase term with a quantized coefficient, which cannot renormalize. And you read these papers if you want to learn more about that. So then, if I want to, you should remember that Q was tau to the alpha, Q bar was tau to the 2 minus alpha. So these have to be equal to each other. You put alpha equals 2 minus alpha, and you get 1 over tau. So that's one way, and really the most general way to get this 1 over tau correlation function, which is believed to be exact, at a possible gapless solution of this type. Now, for the model that I've just described, the insulating antiferromagnet, this solution is not believed to be the answer. And that, because to get the right answer, you have to match not only the exponent, but you have to match the prefactor and all the short time behavior. And for some reason, that match doesn't seem to happen for this model. It's actually a spin glass. But what we are saying is that maybe it happens elsewhere. And that will be the next part of my talk. And I'm almost out of time, I think. Can I have 5 more minutes, Lucia?
Yes, you can. Well, we have the technical problem in the middle of your talk, so I will grant you 10 minutes or 15 minutes more.
Oh, okay. Thank you very much. I don't think I will need that much, but that's famous last words. All right. So now let's do the same tricks for the TJ models. You have Tij and Jij. And now that, unlike 2 states per site, you have 3 states per site. Okay. So it turns out that it's a very simple way to think about this problem. Just by thinking of these 3 states as the states of a superspin. So previously I had a spin with 2 states and a Berry phase term. So here I have a spin with 3 states, which are empty spin up, spin down. And there's a corresponding Berry phase term of Berry that you can write down. But there's of course, one very important difference is the statistics. That is, if you use the slave particle representation introduced before, if you write the spins as fermions and the holes as bosons, then this state is a boson and those 2 states are fermions. So there's some spin that can rotate between these 3 states. And that rotation group is now a supergroup. It's not a ordinary group. And what kind of supergroup is this? Well, if you have 3 states and you're doing ordinary bosonic rotations in 3 states, you'd get the group SU3. So this turns out to be what's called the group SU1/2. 1 + 2 is 3. Just telling you that one direction is bosonic and 2 directions are fermionic. That's all. But other than that, the whole formalism for the TJ model is almost identical to the formalism for the J models. All right. Another cute thing, and this is very important for the final result, you can do the opposite. You can use what are called Schwinger bosons for the spins and fermions for the holes. And you can show this also reproduces the correct algebra. So this will be a superspin with the group SU not 1/2, but 2/1. And then if you open up the textbooks on supergroups, you find actually these are the same group. So that confirms our intuition that you could have made either of them bosons or fermions, but as long as they have opposite statistics, you're getting the same problem. So now what do you do? Well, I've just only show you one equation. It's exactly what you did for the J model, except integrating over a spin, you integrate over superspin P. So this P lives in this supergroup. This is the Berry phase term. And there's some retarded interaction Q, which is now a matrix. And you can determine the different components of the matrix self-consistently. But the one important difference is now there is a field, a term linear in P. And what is this S0? Well, this is just like a Zeman field, which changes the energy between the bosonic, between the hole states and the fermion states. So when S0 is less than 0, then the spin-ons are lower in energy. When S0 is bigger than 0, then the holons are lower in energy. So this is an additional term that you find. So what does the RG flow look like? Well, there's these exchange couplings and T couplings which flow to a fixed point. And that's exactly like the Bose-Condo problem. But you have this new coupling S0 which flows away. And there's a critical point at S0. So this is then our critical point at S0 = 0 that we are really after. And this horizontal axis is just the doping, the density of holes. So here you have more holes, here you have less holes. And this is the critical point. And this critical point has lots of nice properties. So let me just describe them. First of all, you'll find that the spin correlation decay is 1/tau. The super spin correlation can all decay as 1/tau. And now this is a rather peculiar sort of result because previously I told you in a Fermi liquid, the spin correlation decay is the square of the electron correlations. But here that doesn't seem to be true. So how do you understand this? Well, you understand this to answer glad questions by fractionalization. If you assume that the electron is split up into a spin-on and a holon, each of which decays is 1/√tau, then the product of the spin-on and the holon correlation function will be 1/tau. And the product of 2 spin-ons will be also 1/tau. So the fact that these power laws are the same is strong evidence that this fractionalization. And I don't have to decide whether it's fermionic spin-on or bosonic spin-on. They're both equally valid representations. These are gauge invariant correlation functions, which have a fractionalization interpretation. Okay, so that's the deconfined critical point. And then another beautiful thing, what is the density here? What is the value of PC? Well, to leading order, that critical point happens when the 3 states are degenerate, when the Zeman field vanishes. What density is there? Well, 1/3 of the sites are occupied or empty. So the density is 1/3. Okay, that's not too far from the 0.2 in the experiments, but it's actually pretty close to the 1/3 in the numerical study of this specific model. Then you can ask what happens when you flow on the right-hand side. Well, on the right-hand side, this flows off to infinity, and therefore this state becomes very low in energy. So what you should do, this is the guess at this point, is you want to make the low energy state a boson and you condense it. If you condense this boson, then basically you break the gauge symmetry. It's a Higgs phase of the bosons, and these fermions become electrons. The density of these electrons is 1 + p, and you get a disordered Fermi liquid with a large Fermi surface. On the other side, you want to condense the spin-ons. So you make them bosons. That gives you a spin glass state. The density of the carriers now the holons, which are fermions, and they have density P. So you have P to 1 plus P from this. All right, so that was all rather quick, but that's basically the end of my talk. I won't say anything about linear resistivity. There's also a way in this model to get linear resistivity involving something that comes out of SYK analysis called the time parameterization soft mode, which you can read about in these papers. Okay, so to conclude, the TJ model is random and all-to-all hopping and exchange displays a phase diagram, which I just showed you, which captures many of the key characteristics of the Cupid phase diagram. I'll mention what they are in a minute. As an optimal doping metal-to-metal deconfined transition with SYK-like behavior, which is also connected to black holes in this picture. And what are the key characteristics of this novel critical point? First of all, the Green's function looks Fermi liquid-like. And if you look at the numerics, there's some marginal corrections there to the spectrum of the Green's function. And the spin correlation decay is 1 over tau, which is this marginal type susceptibility. These two behaviors can be interpreted in terms of fractionalization right at the critical point. There's no fractionalization away from it. And there's also linear anti-resistivity. That's a possibility, but I didn't describe it. And finally, there seems to be an argument, although not a proof, that there's a jump in the carrier density from P to 1 plus P right across this critical point. So thank you very much. And this is, of course, the other model that I talked about. But I'm happy to discuss either of them with any other questions. Thank you.
Thank you very much, Subir. If anyone has a question, please let us know.
Subir, I have a question.
Sure.
Is this, is the Fermi surface size, does it reconstruct discontinuously from being a large 1 plus P to P at some critical U or whatever you are tuning?
You're referring to the random model?
Yeah.
Well, I mean, it's a random model, so there's no Fermi surface.
No, I meant the one with the fermions and the randomness in the JIJ.
Yeah, so this is the phase diagram that I've shown you here as a function of P. Okay, it's a surmise here based on the RG. So what's happening here is there's an RG flow away from this fixed point. What's going on here? Okay. Yeah, so there's RG flow away from this fixed point. When you flow to the right, you can make an argument that you end up with fermionic carriers which carry spin. So they have density 1 plus P. When you flow to the left, you end up with fermionic carriers which don't carry spin, but the spins are frozen. And this has density P. Yes, so the claim is that at low enough temperatures or low enough frequencies, you will see a discontinuous change.
Okay.
Properties
that was exactly my question. So
yeah.
Basically, once you have flowed to that fixed point, the size of the Fermi surface is a property of that new fixed point it has flowed to.
Yeah, so there's, in principle, I mean, of course, for a random system, a little tricky, but there's a discontinuity in, say, in the Hall coefficient, or for example, the gamma value of the specific heat in this case. Although I don't know, there may be some extra contribution of specific heat in the spin glass phase that we have to worry about. That could be tricky to tell that apart.
Right, but is the entropy, because before there was a lot of entropy system in the Fermi surface, right? Now that has gotten reduced. But where is the entropy going?
Well, I mean, so actually that's another interesting question. So out on this side, it's a Fermi liquid, which has zero entropy at zero temperature. But there's a specific heat coefficient gamma, which will be characteristic of the large density of fermions, of the density of states of Whereas here, again, the entropy would go to 0, but you would have a temperature-dependent and linear in T behavior, which actually is characteristic of small density. But there'll be some other entropy from the spin glass fluctuations, which is could also well be linear in T, I think, which is quite hard to figure out. That requires doing an analysis of replica symmetry, broken phase. However, at this point, in this particular model, you in fact have a non-zero entropy. So the entropy is maximal. If you just measure the total entropy at some given temperature, we predict it'll have a maximum near PC. So this is an SYK like critical point, which has this property of zero temperature entropy, which will be present here. And there is some, not very strong, but there's some numerical evidence for that in this work by Henry and Alex that I didn't talk about.
Okay, thank you very much.
Sure. Okay, other questions? All right, then is everyone still around?
Yes, I think so. Well, thank you very much, Subir, for this nice talk. And we hope to see you again next week. Next week we have Ana Maria Rey. I hope you enjoy your talks and see you next week. Bye-bye.